Complex numbers, 4-4, notes and guided practice. Okay, so complex numbers are our imaginary numbers. That's, the square root of -1. But we're going to learn how to deal with that because I equals the square root of -1. Okay, we need that. Okay, so simplifying square roots of negative numbers, that's our example 1. And I always look at it and say, ooh, that negative says, hey, I need an I in front. And then 27 is 9 times 3. Oh, I can do the square root of 9. That's 3. So 3i times the square root of 3. So simplifying means I might have a square root left. Okay? Negative 216. The negative says, ooh, I'm going to have an I in front. 36 times 6. Sometimes you have to do some prime factorization to find out numbers you need. Okay? The square root of 36 is 6, so 6i times the square root of 6. Guided practice, negative 18 means I'm going to have an I in front. Okay, negative 125 means I'm going to have an I in front. All right, powers of I. This is really cool because we know that I is the square root of -1. So if I have I squared, that's -1. I cubed, that's -I because that's really -1 times I. I to the 4th equals 1 because -1 times -1 is 1. Okay? And here's the next set. Now, the reason I went 4 columns is because if it's even, but not a multiple of 4, it's equal to -1. If my exponent is a multiple of 4, it equals 1. Okay? That's why down here when it says I to the 31st power, well, I to the 32nd, that's a multiple of 4. That would be a positive 1. So that means this is going to be a -1 times I. Okay? Okay, so example 2 deals with products. -5i times 3i. Put the like things together. -5 times 3, I times I squared is -1, which cancels out that negative in the front. Okay. Same with radicals. I got to pull out those i's. This is going to be an I. This is going to be an I. So I'm going to have an I squared. 6 is 2 times 3. 15 is 3 times 5. I got 2 3's. I can pull out a 3. Okay, and that's kind of usually how I do it. Guided practice. 3i times 4i. Well, that's 12i squared, which is -12. -20 times -2. Well, I'm going to have an I here and an I here. Ooh, that should be an I squared, so that should be a negative. Careful, I made a mistake. Okay, 20 is 4 times 5. 4 is a perfect square. I can do the square root of 4, so that's going to be 2, but it should be I squared, so it really should be -2 times the square root of 10. And we talked about that one. Solving using the square root property. Okay, this is, remember we said this is a sum of squares, and it's prime. It has no real roots, but it has imaginary ones. And this is where I am going to subtract 64 from both sides and do the square root. Notice it gives me a plus or minus 8i. Okay? Divide out that GCF first. 4x squared plus 100 equals 0. Divide out the 4. Subtract 25 from both sides. Take the square root of both sides. X equals plus or minus 5i. Subtract 4 from both sides, take the square root, x equals plus or minus 2i. Part 2, operations with complex numbers written in the form a plus bi, where a and b are real numbers and can't be combined. Okay, these are really kind of cool, and it's kind of interesting because you know what? Example 4, you've got these equations. Well, 3x minus 5 plus the quantity y minus 3 in parentheses times I equals 7 plus 6i. Well, these are real. These are imaginary. This is real. This is imaginary. So it's just got 2 parts. You're going to do the real part. You're going to do the imaginary part and put it together. Well, you just had to find x and y. Okay. So the reals go together, the imaginaries go together, x equals 4, y equals 9. Adding and subtracting complex numbers, that's just combining like terms. I tend to do vertical. 5 plus 2 is 7. Negative 7i plus 4i is negative 3i. Distribute the negative and then line up my like terms. Okay, that's just how I do it. Okay. Those I think are pretty doable. Electricity, because I equals impedance, they use J instead of I. But J is just like I. So when you have a J squared, that's like negative 1 squared, or like the square root of negative 1 squared. So it cancels out that negative. Okay? You might get one or two of those. Conjugates have a product that is a difference of squares. This is our conjugates pattern. That's important because I have to rationalize the denominator. I can't have an I in a denominator. Okay, so I have to use conjugates to help me. Okay, so knowing that A plus BI times A minus BI is going to give me that difference of squares. Ooh, but I have an I squared, which is negative 1, which makes it A squared plus B squared, which is a real number. No I. Okay, so in example A, 2i over 3 plus 6i, I have to use the conjugate, which is 3 minus 6i, and whatever you do to the bottom, you got to do the same thing to the top. Okay, but that's going to give me my difference of squares, or really kind of a sum of squares on the bottom. Okay, and then I just distribute on top. 2i times 3 is 6i, 2i times 6i is 12i squared, which becomes plus 12. Okay, and then you have to simplify, and you've got to break it apart. A plus BI. Your answer is a complex number. It has to be the real plus the imaginary. Okay, real plus the imaginary. Now, notice this one only has a monomial in the denominator. I just have to get rid of the I. So I multiply by I over I, which gives me a negative 5 in the denominator. Okay. And then I just distribute it on the top. Okay. So, and then you simplify. Okay. Hope this helps you a little bit. Watch it as much as you can. I hope to be back soon. We'll see what the doctor says. Take care. Bye.